I was muted again. Hello world. Had to do it. So I believe that my screen is not shared yet. I'm gonna share my screen now. And we'll be ready to rumble. Yeah, so it's on, it's on the iquhack, exactly. But all right, let's just get to business because we have a lot of stuff to cover. Programming neutral atoms it requires concepts. so we're gonna go through concepts here, okay? Through concepts with me and through practice with Phil. Okay, that's more or less how we're gonna do this. Again, welcome everybody. For those who doesn't know me, I'm Pedro. This is Phil. I'm sharing my presenter mode. Madonna de Cristo. How do I do this, right? So swap displays. No, that now everybody here is seeing the other. It always feels bad, right? Like it feels like somebody's seeing you in your underwears or something. It's like a funny situation. Don't look at my screen, please. Not any better, right? Not any better. And then Zoom decides to put the stuff, a recording present. I guess that makes sense, right? Just share the whole thing, and we'll go for it. Yeah, but now this thing, how do I get it? Oh yeah, I see. I have to. I went there. We good? We're good. Oh la la. All right, let's do this. So, introduction to quantum computing with neutral atoms. Me and Phil. Let's get to business. So, neutral atoms is a new-ish technology for quantum computing. This has been on the works in the shape that it's taking now for the past about 8 years to 10 years. It's been like a tremendously fast move between academia and just 3-5 years later, they were having first an empty optical table. Then suddenly there was a computer. Suddenly there was Nature and Science papers. Suddenly there was a company. Suddenly this company puts a computer online, right, for everyone to access. That's us, right? So it's very recent, but yet at the same time, it's becoming a major contender for the technology that will allow people to really solve interesting, useful problems. And there's a set of different reasons. Maybe some of them you are aware, and that's the reason why you're here. Quantum computing with neutral atoms allow you to, atoms are pretty cheap as qubits, so you can get lots of them. They're all equal, so you can densely pack them together because they're neutral, so they don't repel each other. So they like to be close to their friends. The qubit control is very efficient because you can use few laser channels to control many qubits, many atoms, right? And as we'll be discussing a lot, there is a lot of flexibility on problem encoding. So pretty much in line with the conversation that we were having the panel for those who were there. This is cool, and I hope that that's the reason why you're here. Because this allows for new ways to think quantum computing. Okay, so things that you will not see here is quantum gates. You will see quantum gates only in contrast against what we will actually be doing and how we have to think about problem solving. Okay, today this is very close to physical thinking. And at the same time, this allows for originality, for creativity, for new solutions, more efficient use of quantum resources, and we believe as well for an interesting path towards fault tolerance and scaling. So to get started, I swear there's going to be only one slide if you're already aware of this, but I do need to get everybody on the same spot. Quantum computing, right, is all about new rules. It's not about computing faster, it's about changing logic, right? So logic for programming, you have some input, you process that information using this logic, the set of rules that allow you to manipulate the piece of information, you get results out. For classical computing, we do bits, 0 and 1, right? Just signals with logic gates, and the result is deterministic. Quantum computing, we use what we call qubits. So these things, they are not just digital, they actually live continuously on space. And we use quantum gates or not, but the logic is based on the laws of quantum mechanics. That's the point. And the outcome of these calculations is probabilistic and deterministic in the sense that the probability distributions are deterministic. Okay. Here's the point where things start to change right away. Okay. So regularly, when you think about computing, processing, you are looking at a minimal set of operations that allow you to do your logic, right? So here we talk about gates, right? Hadamards and gates for entangling, 2-qubit gates, et cetera, but that's not the only way of operating qubits. And in fact, if you study quantum mechanics, what you learn is that this is just a time-dependent process. You're just evolving a set of quantum states in time. You define them in the beginning, and you want to control them in some way through what's called a unitary evolution. Okay. This gives rise to a different mode of operating quantum computers, which is this thing called analog operation. Analog operation here means have one large gate that controls all qubits at the same time, right? And that you can control continuously in time. You don't need to discretize it, okay? So this is pretty cool because you save on errors, because the beginning and end of every gate leads to errors, and because if you are doing problems like time evolution, time-dependent phenomena like simulations, if you ever heard of trotterization, you don't need to trotterize anymore. You just evolve things, and there is no trotter errors anymore. So this saves on errors. Okay, so when thinking about using quantum resources, and I think everybody that has ever tried a quantum computer today here have realized quantum resources is a limited commodity. You try to use them. If you don't use well, noise will break everything. Okay, so you want to use these machines in the best possible way. And this analog mode is more economic. It allows for easy control because you're controlling everybody at the same time with few channels. And it allows for things like single-step entanglement, so preparation of large entangled states all at once. Of course, there's a downside, right? How do you make this universal? In principle, if you can control this matrix here in any way, you can make it universal, but that requires a lot of complexity. So these machines are not born universal. These machines are born scalable. And universality is being brought step by step instead of scaling being brought step by step. Okay. It doesn't mean that we cannot do anything about it. Okay. And one thing that we do at QuEra is have this paradigm that you cannot see because some participant has enabled closed captioning. People can see this transcript recording on X. Is this paradigm of field programmable qubit arrays. So some of you might have studied engineering or might know a little bit of circuits. You might have heard of FPGAs, right? So field programmable gate arrays. So these are chips that you can reconnect the transistors in them in a way that is adapted to your problem, making them highly efficient at solving your problem. A field programmable qubit array is a quantum computer where the connectivity of your qubits can be redefined by the users. Right? So for example, you can take your qubits and put them in a hexagonal honeycomb lattice, but you can put them in a square lattice. You can put them in things that don't look like lattices. And what happens here is that controlling qubit positions allow you to control their connectivity and allow you to have many possibilities of thinking problems and solving problems using geometry in your favor. That's something that if you print your qubits in a chip, you're going to have a hard time of doing because the chip has, I cannot do this with this laptop either, right? It came as it is. So this is a way to address this universal applicability problem. I'll give you an example of what you can do with it. Let's say you work for Dunkin' Donuts. You may have gotten promoted or demoted, right? And somebody gives you the challenge of covering Boston with Dunkin' Donuts. It's more or less already solved, right? But maybe the solution that exists today is not a good one, right? So what you can do is you can put on the Boston map your qubits and create an atomic twin of Boston. You can literally do that with atoms. So these are atoms. These are individual atoms put in place exactly according to this graph. And try to ask, how can I put as many Dunkin' Donuts around in a way that I don't have too many, right? Because if I put one neighbor into the other, then I'm not selling well. I want to keep my Dunkin' Donuts more or less far apart. It's like Starbucks in Seattle, right? Not in Boston. Not in Boston. You want more Dunkin' Donuts. Oh yeah. Maybe you should contact them, right? So you can do the calculation. So this is pretty much qubits being excited or de-excited. And you can find the solution right away, just because you were able to put your system, your processor in the shape of Boston. Okay, so that's one type of application. You can do more things. You can do parallelization. You can create subprocessors. You can do many things. There have been many major victories of the platform. This is not just about QuEra. This is not just about our friends, but evidently there is a little bias here towards our collaborators, right? So the creation of extremely large phases of matter, the control of the dynamics of this phase of matter. So I want to emphasize that while some of the algorithms that we will discuss here are adiabatic, read annealing, this system is not an annealer. You don't need to anneal. You can do QAOA, you can do pulses, you can create a bunch of things. And we are certainly hoping that through the next day or so, many of you will be trying different things with this. There's been the creation of things like spin liquids. So spin liquids is a little bit technical. It's very relevant for condensed matter physicists. But let's just say that it's been a very complex quantum phase of matter, okay, that has been searched for many, many years, decades, without anybody being able to realize them until this platform was. And of course, this has had decisive contributions from QuEra, the optimization problems, solving optimization problems, this thing called maximum independent sets, that again will serve as an example for today. Okay, motivation gun. Let's talk a little bit technical stuff. How do we make qubits? So qubits are made by puffing atoms. So making atoms that are tiny, chubby, okay? So for us, depends on the company. Some use rubidium, some use cesium, some use ytterbium, strontium. We use rubidium, okay? You don't need to know which electronic levels go in here, but the point is rubidium is in the first column of the periodic table. It's an alkali atom, so it has a single electron. This is just a heavy hydrogen atom, okay? And we are gonna take this electron, this one electron that is in the valence shell. It's gonna go from the ground state, where the atom is pretty much angstrom size, to a shell that is principal quantum number equals 70, okay? So this process makes this atom increase pretty much 1,000-fold. When it increases 1,000-fold, it becomes highly polarizable, like dipoles, and then it's capable of interacting with neighbors. So this is how we are encoding qubits today. So ground state is a 5s, Rydberg state is a 70s state. 0, 1, okay, for the purpose of our next 2 days. Algorithms, right? So algorithms in quantum mechanics are just time evolution. Whenever somebody is giving you gates, they're just hiding the fact that they're making a time evolution. So if I've never seen this, this is a time evolution operator in quantum mechanics. And they're just evolving that for short times in a way that is going to operate in a little bit part of your Hilbert space. Here, this thing is global, general, and there's this function called a Hamiltonian, which for all practical purposes, you should think of a cost function for energy, okay? That is going to control the system. So knowing the Hamiltonian allows you to control your qubits, allows you to control and do calculations, okay? So you need to know what's the Hamiltonian, what is this cost function. Again, think of energy. And here we go. So you guys should know the Hamiltonian. This is what it looks like. Hopefully the symbols are not Greek. Some of them are. This was not a failure, this was on purpose. So what you'll be doing is you take your atoms, you position them in a 2D plane, okay? Doesn't need to look like a lattice. I'll say it again, doesn't need to look like a lattice. And if, to make sure I make my point, doesn't need to look like a lattice. Here's a lattice, okay? So there's gonna be a laser beam that, or more technically, that's gonna shine the plane of this lattice. And this laser beam is going to be responsible for flipping qubits from ground to Rydberg. Okay, from ground to Rydberg, from 0 to 1. Okay, this guy, this laser guy here, is that omega over there. Okay, the first term that that you have control over. Sorry, you have a question?
Yeah, I wonder what is phases on both the projectors, the GR and RG. Could you multiply it all by e to the IPT and have a phase just on one of them?
You can.
Phases.
Yeah,
They're Hermitian.
They're Hermitian. So, so the point is that omega over there does not depend on this sub-index I. Okay, this is a single laser that shines over everybody, so everybody's entangled together. That's important. Everybody's entangled together. Our machines, the one that you have access, can operate up to 256 qubits. Okay, so this is as large as you can get, pretty much. But all of them are operated together. So you can control that thing depending on time, omega. You can control this phase depending on time. Next thing is these guys here. They're called detunings. Oh, by the way, whenever you have questions, you might have us answering, talking about Rabi phase or Rabi term. So that omega is a Rabi term. It's what creates Rabi oscillations between energy levels of your qubits or between your qubit states. These deltas are called detuning parameters. They're also controlled by this green laser, except that it's more like a shifting phase in frequency of the laser. And what they do, so that N over there is 0 or 1, depending for 0 in the ground state, 1 in the Rydberg. So this means that everybody that's on 1 gets penalized by delta, or anti-penalized if delta is negative, okay? And that's it, and you can control that in time. So whenever you're programming, omega and delta are the things that kind of define what is the gate that you're operating on your system. There's a third term that is nevertheless probably the most important. That's the interaction term. Okay, so that thing when N, I and Nj are 0 is 0. When one of them is 0, it's 0. When both of them are 1, you pay Vij. Okay, Vij goes as a constant divided by the distance between the qubits to power 6. We can discuss through the weekend why that happens this way. What matters is just that entanglement is position dependent. So by defining the position of your qubits, you are also controlling this term of the Hamiltonian. Okay, so 2 time dependence, 1 geometrical. Okay. Any questions here?
So this is 3 degrees of freedom that you're controlling?
Well, this is time dependent and it's pretty free in time. So it's actually more degrees of freedom. Also, the position of each atom is a 2D vector. So we have 256 times 2, 512.
This is like in SC2D, and you have like, well, you have exponentially many degrees of freedom, right?
Yeah.
So how do degrees of freedom?
So you don't have access to the whole Hilbert space. You only have access to the useful part of the Hilbert space, or a useful part of the Hilbert space.
Yeah.
Right.
So you mentioned earlier with this that you don't have to charterize or something. I can kind of see that here, but with the way that things can be studied with the Vij term being like 10 to the 6 based on the distance between qubits, do you not need to charterize for only problems? You don't have to charterize for only problems that embed to a planar connectivity graph?
Yeah, so you can definitely charterize.
So if
Okay.
you had a problem where that did not embed to a planar connectivity graph, then we would have to charterize.
It's possible to do. You don't need to charterize to do that. There are methods. So I might have. I don't know if I put the reference here. We have a paper where we use something that we call gadgets. So we create clusters of qubits that have a certain weight in energy that can be used to encode, for example, crossing between edges of a graph. So we still don't charterize necessarily. Okay. For the interest of time and to not to get Phil running, I'm going to keep moving. But we can talk more later. Paradigms for algorithms. I want to emphasize this doesn't need to be annealing. Okay, so state preparation. Okay, quantum dynamics, We can do optimization, we can do machine learning, we can do sampling, we can do simulation, we can do the dynamics of systems that is more applied for quantum simulation or machine learning, okay? In these paradigms, I think that it's important that I give you a few more concepts that will probably be useful through the weekend. This is called a participant has still have enabled tab. Okay, Rydberg blockade phenomenology. So Rydberg blockade. Okay, so what's the Rydberg blockade? Rydberg blockade happens as follows. Imagine I'm going to give you two atoms. Okay, just for the sake of argument, a distance d apart, and I'm going to give them a detuning. So this means that everybody that has one Rydberg excitation pays delta. So I have two of them here. So it's 4 states, 1, 2 here. The last one has RR. Both of them are in the Rydberg. So it's a 1, 1 if you want, logically. This pays 1 delta, 2 delta plus a V. Okay. Now, what is interesting about this situation is that if I push these atoms together, bye-bye, right? Right, it went to SpaceX. You completely expel one of the states from the Hilbert space. Of course, that there's energy scales associated with this. So depending on the strength of your omega, you know you're going to have to play with that. But the point is that you are able to control locally what kind of states are part of the Hilbert space in your problem. And I'm going to show you an application in just a second. Just before that, I want to give you another concept that is related to it, which is the Rydberg blockade radius. Imagine I'm going to turn off omega for simplicity. Okay, I write the matrix associated with that Hamiltonian. It's not so hard. N is a good quantum number. Everything is in diagonal, right? 0. So this is 0, 0. This is 0, 1. This is 1, 0. This is 1, 1. Okay. So pretty much the middle ones have the delta, the other one has 2 delta and a V. So when you look at the energy of these states as function of distance d, you find that there is a moment where the energy of this bottom state crosses that the middle ones. So you can equate these things and define a length scale, and this is called the Rydberg blockade radius. Okay, so this is fixed by the energy of this delta, and this Rydberg blockade radius is pretty much a characteristic distance between for which if atoms are closer than that Rydberg blockade distance, they cannot be excited both at the same time. I think I have a question over there. Oh no, just okay, dropping the pressure. Does it make sense? So the Rydberg blockade radius is the radius from which this happens. Okay, is the characteristic distance after which you really expel one of the states of the Hilbert space. What do you do with that? This is the kind of the basic language of quantum computing with neutral atoms. Okay, this is called the maximum independent set problem. So forgetting all quantum computing, let's go back to just regular graph theory and computer science. So you have you're given a graph, okay, with nodes, vertices, painted white, and I'm going to ask you to paint them in red under the constraint that edges, vertices that are connected by an edge cannot be painted red at the same time. Two of them, if they're too close or if they're connected, they cannot be both red at the same time. This is an NP-complete problem. Okay, asking for what's the largest such state is an NP-complete problem. And you can start imagining already what happens here, right? Like if I have atoms, they are close enough. If they're close enough, I can imagine in my head that there is an edge between them, right? And if I try to excite them both at the same time, voila, I cannot paint both Rydberg at the same time. Makes sense? A little bit, hopefully. Questions? This is important.
Sorry, can you repeat that last bit?
Yeah, absolutely. So let's encode these vertices in a way that 0 means ground state, red, right, 1 is the Rydberg state. I just showed you that when my Rydberg states are too close from each other, I cannot have Rydberg. So if states are too close to each other, they cannot be read at the same time. Therefore, by taking a collection of atoms, right, and trying to push them into all be excited, if they are close enough, I have a constraint that is going to say, oh, only one of them is going to be excited, and the others around them will not be excited. Okay, so this Rydberg constraint is directly encoded in the system.
So what if the graph is not
This graph these graphs are not planar. Okay, so these graphs are known as unit
Unit graphs.
No, I know. Yeah, I always get confused with the nomenclature. They're not planar. Okay, they don't live in a plane because there's crossings. Okay, so they're called unit disk graphs, where the unit disk. So this means vertices that are connected whenever they are within a radius unity of each other. It's a unit disk graph. The unit disk radius for us is the Rydberg blockade radius.
How is it different from max then? Isn't that like two nodes that are next to each other, they cannot be Rydberg, but they can be like
It's slightly different, right?
Yeah.
You have a
it's
comment?
different, but I'm not going to comment. I'm not an expert.
Let's chat
Yeah,
through the weekend about that. Okay, just to not derail. We keep going. So an algorithm for doing this could be as follows, right? This is a diabetic algorithm. Okay, so I can start with my delta very negative, which means that any guy trying to excite to 1 is going to pay a lot of energy, right? So everybody's happy being at 0. Everybody's happy being white. Okay. Then I'm going to start climbing this delta to make it more and more positive, so that atoms will be happier if they are actually excited into the Rydberg state. And of course, I have to enable bit flip. So enabling bit flip means taking this omega, climb it up, and keep it there. Okay. How much do you climb it? Climb as much as you can, because this omega defines how fast your oscillations are happening, how fast the scrambling is happening. Okay. And you stop that delta pretty much such that the final value of delta fixes the Rydberg blockade radius that gives you the graph that you're looking for. That was long, but you stop your final delta such that you fix the blockade radius so that your bunch of atoms, your collection of atoms, describe the graph that you're looking for. Okay, so say, oh, I want this graph, this node to be connected to that. Oh, I need a Rydberg radius of yay big, right? And then I say, okay, so now delta is fixed, and then I can ramp until I get to that delta. Adiabatically, this collection of atoms is going to grow, boom, and it's going to finish with as many Rydberg excitations as allowed by the constraint of their positions, their distance to each other. This is, yeah.
Well, can you go back?
Yeah, evidently.
So, as I understand, it depends on the problem itself, and that red and blue areas that we define with the radius, what we call.
The edges you define by the radius.
But it's not the only solution, right? We can create more solutions.
There, you can create more solutions.
And that will give you another different.
The maximum independent set is not a unique state.
Oh, okay.
Okay, it's degenerate. It's definitely degenerate. Okay.
How do you control the, I guess, what did you call it, the detuning? Correct?
Yes.
How do you control that?
How do you control that? That is controlled by slightly shifting the frequency of the lasers, but that's why we call detuning. They go out of resonance, and that causes a penalty for exciting atoms. Pretty much, that's how it happens physically at a laser level. Okay, so the bottom line is that this is highly applicable. I strongly encourage you, if you're curious about what you can do with this, to check. There is many graph problems that can be mapped to independent sets, and this can go from placing antennas, placing Dunkin' Donuts, placing antennas in a place, because if you put antennas too close together, their signal jams. But if you are too sparse, you cannot call home. You can place houses. You can even do things like optimization of financial portfolios and more. Okay, so there's lots of applications for this. And I'm about to send this to Phil. I'm 7 minutes and 40 seconds late. there's 5 steps for this. First, choose where you put your atoms. Second, define the time dependence of your Hamiltonian. 3, 4, 5 is just the standard. Initialize Hamiltonian, evolve measure. Okay. So 1 and 2 might be different. 2 is different because this is analog. 1 is different because you actually get to choose. Okay. Thank you very much, Phil.
All right. Thank you so much, Pedro. So. Let me get it set up. Good.
I forgot if there's questions from the audience online, but
Oh,
let's make sure we ask them
we
later.
have a MC.
Shantanu. Okay, cool. I really hope I haven't been.
Yeah, you have. That's
okay.
That's okay. There was the subtitles.
Yes. So my apologies to the audience online. So now we have a conversion factor to convert between the unit disk and the physical length scale, which is associated with our blockade radius. So let's use this conversion factor to generate our program. So for that, the thing that you will be using to generate the geometry of your atoms is an object called atom arrangements. It's basically just a collection of positions in a plane. So in this case, I take my positions from the graph. So in this case, the positions are the graph of my problem. And then I scale it by this factor A in order to make it graph our positions in the actual physical space, which will be our quantum processor. And I do this for all of these things, all of the positions in the graph. Another thing I'd like to advertise is this package called QuEra AHS Utils. It's a Python package that you can download, and it has some functions that will be useful for analyzing, visualizing, as well as just programming our device. So in this case, I'm using one of the visualization tools, which is show register. And you can see now what this tool does is it plots the positions of the atoms. Oops, well, it's not fitting nicely in here, but it plots the positions of the atoms. And if you go to blockade radius, it will actually draw edges between nodes or atom positions that are within the blockade radius. And so with this, we can confirm that indeed we have the same graph with the edges that are within the blockade radius. And now you see my scale is now 10 to the minus 5. So this has been shrunk down to the size of atoms that we can actually program on our hardware. So great. Now let's do the adiabatic protocol. In this case, we will exploit what is called the adiabatic theorem. I'm not going to go into too much detail here, but it's kind of the main driving principle behind a lot of quantum devices like quantum annealers. Although in many cases it's, so for example, I would definitely suggest if you were to play around with our device to do not do the adiabatic protocol, and you can do all sorts of interesting things with the pulses here. But just as a demonstration, we'll show what the adiabatic algorithm can do for our problem here. So this is a relatively small problem, so I'm gonna spoil things a bit. It's gonna be pretty decent, but when you actually start to scale things up, the adiabatic protocol is not gonna do so well. So how do I define my sweep? Well, it's a piecewise linear function for the omega, the Rabi frequency, and the detuning delta. And then for the phase, if you're wanting to work with the phase, the function that you get is piecewise constant. So that being said, how I define my protocols are basically I have a list of times, and then I have a list of values that are associated with each time point. And then the program is just doing either a piecewise constant or a piecewise linear interpolation between those points. So the protocol is relatively simple here. And because our drives are effectively correlated, right? When I turn on my Rabi amplitude, I keep my detuning constants. So because of that structure, we built the helper function to basically generate all of these curves simultaneously, since they all have the same time points, but that's not actually required. Each one of these pulse sequences can have their own independent set of time points. It's just in this case, it was very easy to just do everything in one shot. So this is the Rabi amplitude, this is the detuning, and the phase is obviously 0. So the values that I pick are related again to the blockade radius. I'm not going to show you what the values are, but it's okay. So it's about 10 million and 20 million for the detuning. But these numbers are arbitrary. You can go up and between the minimum and the maximum values allowed. And depending on what you want to do, you might have different blockade radii for whatever graph you want to do. Okay, so we have our atom geometries and we have our pulses. So now we need to just put the finishing touches. Yes.
Yeah, I have a question. What's the effect of the phase on this? Like, Yeah, that's a good question. So basically, imagine like you're switching, you can switch between whether or not you're doing bit flips with, I guess, basically a sigma X term, or you can do a sigma Y, right? If you turn my phase to be exactly pi, then I can do something like a sigma Y kind of bit flipping. So it adds some extra phase to it, or an extra complex factor to it. And then you can also do somewhere in between. So you can actually, because it's a continuous function between 0 and pi, you can actually use this to do kind of like interesting protocols where you will drive maybe the sigma X and drive the sigma Y in you know, discontinuous or smooth, however you want to do it. There's a few reasons why. So for example, there are some methods which allows you to go beyond the adiabatic sweep, which involves driving the sigma X and the sigma Y in like a periodic manner. And through like some effective, I guess, in this case it's called flow K, you can actually effectively drive the system in a way that would counter the diabatic effects that you have from your protocol not being finite or not being infinitely slow. It's called counter diabatic driving. So that's one interesting thing. You could also do something like QAOA, which is kind of a related algorithm where you basically use a classical optimizer to try and figure out a pulse sequence that will reduce these diabatic effects in your protocol. I hope that was somewhat helpful. Okay. Right, so we have our program, we have our detuning, Rabi, as well as our phase. And then we just package these two things together with the geometry, these three things together with the geometry to create our full Hamiltonian simulation program. And you know, it's very aptly named, Analog Hamiltonian Simulation. Now that we have our program, we can now use our devices to run the program and do either the simulation on the hardware, well, it's not really run the program on the hardware, or in this case, the Bracket folks have been nice enough to provide a local classical simulator that can run on your laptop to do basically a test run of your program. Now, just warning you, you can't really go beyond, let's say, 15 atoms, but it's still kind of useful for you to play around with to understand what's happening in these programs when you develop them. So in this case, I haven't been executing any of these things, so I'm going to go back. Sorry, guys. Execute. Aha. Spend too much time coding in VS Code. I don't even know how to do Jupyter anymore.
Spend too much time looking at Jupyter, I cannot do VS Code.
Okay, so we've created our program, right? So let's call the local simulator. So I've written some functions to save data to JSON, which is going to be pretty useful for analysis later on. This will actually give you a sense of what the results look like when you get them back from the AWS task. So in this case, I create a task by calling device.run of my program. And of course, as Pedro mentioned earlier, these are quantum mechanical programs. And so you're not going to get one result, or you're actually want to sample from some probability distribution. So you're going to want to run your program a few times in order to actually understand the statistics of your actual distribution at the end of your protocol. And so in this case, I'm doing 1,000 shots. Although what I would recommend is that, just to make sure that we don't overuse the machine, when you do tasks for the challenge, please limit it to be within 50 and 100 shots. So no less than 50 and no more than 100.
In other words, we will strongly discourage you, okay, when evaluating your solutions if you're using too much, because you get in the way of your friends, right?
Right.
Right.
Yes.
So
it's a very limited resource.
It's a strategy for competition, but that's not a nice one. Okay,
so if you have a simulator, run as many shots as you want. That's fine. But just when you're actually running the hardware, please limit the number of shots. Okay. So here I run the task and I get the results. I'm going to save it into this JSON file.
For the simulator, you can use as many as you want.
Yeah, exactly. 1,000 shots is
It's your
fine.
laptop. Torture as you wish.
And so now let's just take a look at some of the solutions that we get out of it. Okay, so not too bad. So what we see is that we actually get independent sets. So that's nice. Each one of these is an independent set, but only one of them is actually the maximum independent set out of the shots. So these are 3 out of 1,000 shots. But you know, that's interesting looking at shot by shot, but let's actually do some analysis to see what are the solutions looking like on a more broad scale. So in order to do this, we should actually make sure that our shots are independent sets. Now I know Pedro said that it was basically a blocker. The blockade radius will mean that it's a hard constraint, but it's actually pretty soft. So there will be cases where you will actually find independent set violations because you haven't moved the atoms close enough together, or you've come up against the hardware constraints. And so one way of actually generating an independent set from a graph that is colored in such a way that does not have an independent set is to just randomly remove nodes or randomly, erase the red colors until you have an independent set. So that's what I'm going to do here in this function. It's just going to be randomly removing them. It's not optimal, of course. You can definitely be a lot smarter about it, but this is just what I'm going to do for this demo. And then after I've processed all of my results to be that I know that I have independent sets, I'm going to plot some statistics. Okay. So I've executed these functions now. So let's open up our data and let's visualize the results, a histogram. Okay. So my apologies for the graphs not fitting on the screen, but you can basically see that. Yes. So basically what you can see is that the adiabatic algorithm actually did not too bad here. So the maximum independent set is 3, and it seems like the probability of actually getting that is almost 1. So good, that's great. We've done some quantum optimization using the adiabatic algorithm. So okay, this is the visualization of those shots. So now let's actually do something a little, well, we don't have that much time left, but basically let's scale this up to now, let's say a few tens or hundreds of atoms. I wrote a code which will basically take the same graph, scale it up to a 15 by 15 lattice, randomly remove defects, do the embedding. We've got the same infrastructure for the small problem that works for the big problem. So this is our graph. So now you can see there's a lot more structure in here. We've got some like loops and nodes that are kind of like nearly disconnected. So let's actually see how this works in terms of the optimization. So to run it on the actual QPU, you go to our friend's AWS device, you plug in your ARN, and then you do qpu.run your program and the number of shots. So in this case, the program is the same program from before, but for now our 15 by 15 lattice.
So that's the 1,000 that you have to be careful with, okay? Okay, so the computer is ours. We get to pick how much we want, but you don't.
Yes. All right. So I've run this before. I've got the data. I'm going to just open up and show some random shots. I forgot to define the graph. Yes. Okay. So I'm not going to run that cell because it won't work. Okay. So here's some random shots from the actual QPU. So you can see in general, the red spots are definitely wanting to be isolated, but there are going to be some violations. So here's a violation, here's a violation, there's some more violations, right? And that's to be expected because this is not exactly a hard cutoff, it's a soft cutoff. So let's do our minimal post-processing again and look at the statistics. So now, okay, we see that there are independent sets, and these independent sets are much larger than before because our graph is much larger, and that's great. And there's a distribution of them now. So the probability of finding a large independent set is actually not 1. It's actually relatively small. And this is typical with an adiabatic algorithm. So you scale up to more and more atoms, the harder the optimization becomes. So you have to anneal for longer and longer times. So that's why I recommend not doing an adiabatic algorithm if you really want to try and leverage the power of Aquila.
We don't not recommend it either.
Well, if you want, yeah. I'm biased because I like dealing with these non-adiabatic algorithms, so I will put that out here. So here's two of the two largest independent sets, and they're actually not the same. If you actually stare at this graph long enough, you'll find some subtle differences between the two. And so in typical with a lot of these optimization problems, there's going to be a large number of solutions. And this is actually not, I don't even think this is the optimal solution. So, all right, I will just end with revisiting the Boston example because I think this is really neat. So the graph that we showed you was, had some structure that was not, that was pretty interesting because of the defects that we added into it. But it's still a square lattice. And the one thing I'd like to emphasize is that you can do irregular lattices with Aquila. There is one teeny constraint, and that is generally these geometries work best if you work with graphs that are in rows. But these rows can have atoms in arbitrary positions. That's more of a constraint of how one actually operates the device. So it's not a fundamental limit, it's just more of how our device is operated currently. But that being said, you can still do some pretty interesting things with Aquila. In this case, map out some points on Boston and try and optimize it. And I have data to show, but I will leave that to you guys to check out later. So thank you very much, and let me know if you have any questions.
Before, big shout out to John Long over there, also from QuEra, for helping us a lot with all of this. Both of us will be around here. All of us will be around here. Now, questions?
Yeah, so is there anything you can tell us about what's going to be different about our problem versus?
Is there anything that
are we allowed to say that?
I think we are not allowed to say anything. So, so you don't even know if it's gonna be about independent sets or not. It doesn't need to be independent sets. We actually do other things, by the way. But Torque, what can we say? You're an organizer. You can say. You can say whatever you want.
That's true.
There might be some state preparation.
There might be some state preparation. Absolutely. So there's, you know what? Whoever has questions, come here. Let's chat here, and remember that there's the QueBraid presentation now as well. So this is what we use to close the live stream. Yeah, are they coming here, right over here? Yes. Or, yeah. Oh, it is here. So there is a whole area called not so many bytes. So I don't know if I've ever heard of this, but it's pretty much